Okay, I appreciate the invitation to speak here, and sorry I couldn't participate in the rest of this workshop, which looks on the program, it was very lively. Today I want to discuss some of our work on Efimov-related physics, and in particular, some of the newer developments are within the past year or so. First, talk about some of the things that were alluded to in Daniel's talk about the effect of the van der Waals interaction in particular, a sort of new specialized type of universality that is only really applicable. It seems to hinge on the van der Waals forces, although there are some analogs for other long-range forces. Then a prediction we made late last year about D-wave resonance physics, three-body resonances with D-wave character. Talk a little about going beyond three bodies to 4- and 5-body recombination resonances, where there's some interesting experiment and theory developments. And then there, if I have time, I'll say a little about some extending confinement-induced resonances, a la Maxime Olshani, to other geometries in the transverse confinement, which has led us into some interesting mathematical issues. Been fun to learn about as well. So first of all, these are the main culprits who helped me to put together this work: Jose Dinkau, Javier von Stecher, Seth Rittenhouse, Nirav Mehta, some years ago played a role in especially the 4-body stuff I'll show and the n-body recombination extensions. Yu Jun you heard from earlier, and Brett Esri, and recent PhD Jia Wang, who's working with Robin Cote at UConn right now as a postdoc. So just to give an overview of what I want to talk about, I want to summarize the philosophy we're approaching these few-body systems, and discuss the recent experiment in theory in the 3-body sector and the role of van der Waals potential, and also these 3-body resonances, which apparently have not been observed yet. It's a prediction at this point. There are also some extensions that Yu Jun mostly spearheaded about extending these van der Waals, the role of van der Waals interactions, to heteronuclear 3-body systems, then the 4-body problem, 5-body problem, and these confinement-induced resonances. And like Selim, we're, I guess, trying to move toward heaps, but it's rather slow because it's about 3 orders of magnitude each time you jump one index in this problem, at least with our toolkit. Mentioning the toolkit, the first starting point really, the point of departure for most of our treatments is the adiabatic hyperspherical representation, which can reduce any n-body problem in Schrodinger physics to coupled equations in a single coordinate, the hyperradius. And this 1968 paper has provided the foundation of the way we're tackling most of these systems. And to kind of draw an analogy with quantum chemistry, there you have sort of the quantum chemistry experts who are really great at solving for the potential curves, potential energy surfaces, using a variety of methods, Hartree-Fock, and then configuration interaction, coupled cluster, DFT, and so on. And then you have another community in the physical chemistry who are good at solving for the coupled equations, the inelasticity, the dynamics on those potential curves or potential surfaces. We would kind of like to see the field move to this point as well in the n-body problem, and have sort of an analog of a quantum chemistry community that could use their computational tools and give us the n-body hyperspherical potential curves. So far, that community is just us, so we have to kind of do both of these. And you know, for the most part, what I'm interested in talking about is not the details of how we actually obtain these potential curves and non-adiabatic couplings. We're mostly going to focus, in this talk at least, about the dynamics on these potentials and not dwell too much on how to get them. So in that sense, I kind of view some of what we're doing as sort of Mulliken style not too long after the Born-Oppenheimer paper in 1927, just a few years later, Mulliken could sort of start drawing potential curves from everything he knew about chemical bonding. He could take some experimental spectra and deduce, for instance, these solid curves, potential curves in a lithium dimer. In some cases, he drew these dash curves just sort of with his head and with his intuition. And in some cases, doing very small-scale calculations, he could deduce a lot about the system. And in some cases, we have to resort to this sort of strategy because we simply can't calculate, really, at the moment, more than about 4 particle potential curves. So, for instance, in the 5-body problem, I sort of view what we did in the theory side as kind of a Mulliken-style combination of intuition and bootstrapping from what we had learned about smaller systems. Again, the general strategy is to single out one fragmentation coordinate. Usually in this talk, that'll be the hyperradius. Find the fixed R energy eigenvalues of the system, and you can plot those. They become potential curves as a function of that one fragmentation coordinate. Then you can solve coupled equations on those and obtain scattering observables, like one I'll show you is a 5-body recombination rate later. And again, we hope we can reach the point where we can keep building our intuition, won't have to put everything on a huge computer. We hope it'll go beyond that point and we can really start understanding qualitatively some of the issues involved. And one of the things that interests me is pushing and kind of like Daniel said, seeing how all of these different systems have some elements in common. So one thing we've been doing recently is collaborating with a nuclear theorist in Pisa, Alejandro Kievsky, along with postdoc Kevin Daly in my group. We've been looking at 3 nucleon potentials. And so, for instance, you see the most attractive neutron-neutron-proton potential curve. In here is sitting the triton binding energy somewhere. And then fragmenting to infinity is a channel, a 2-body deuteron plus neutron channel. And you could see, for instance, in this how 3-body recombination would have come from coming in on the 3-body, one of these infinite number of 3-body continuum channels, and having a non-adiabatic coupling drive you into a recombination channel. And we're just in the start of studying these kinds of processes, but I'm kind of intrigued to see how far this universality goes. Just kind of a hint of what I'm going to show later is, again, in cases like where we can't calculate the 5-body potential curve, like here for 5 free cesium atoms, we, again, try to bootstrap from various pieces of information. What is the topology? What is the shape of the potential curves? How big is the potential barrier? And in collaboration with Javier von Stecker, we were able to deduce a lot about this and make some predictions about the nature of 5-body recombination in an ultra-cold gas of cesium. So let me give a very brief overview of some of the relevant Efimov physics for this talk that you need to know. Most of this was already covered by you, June. But let me remind you that if you look on sort of a square root of energy scale, sort of a 3-body wave number scale versus inverse scattering length, then the dimer energy maps onto a straight line on this plot, because as we know, the energy goes like 1 over a squared. And so what we did in the late 90s, when it became apparent that 3-body recombination was the dominant way that atoms are lost in typical Bose condensates, we, especially with Brett Esri and the student at that time, Jim Burke, we basically dove into this hyperspherical problem and started mapping out what 3-body recombination rates looked like versus scattering length. And we found some of the features Daniel alluded to earlier that are now understood in other ways, as well as this hyperspherical picture. In our picture, we see a Stuckelberg minimum, which is a multi-channel, a 2-channel interference minimum. We see an infinite sequence of 3-body shape resonances which are the Efimov states, the states of Efimov character. Someone once told me we didn't cite Efimov in this paper, and I looked and I noticed, yeah, we didn't actually have a citation to Efimov's paper. It was like when we wrote this, we thought, oh, Efimov physics is so well known, we'll just, talk about it like the Fermi golden rule. So we did mention it actually in the paper, but not as an actual reference in the reference list at the end. But his work really obviously inspired us, his 1970 paper in particular. And this is the energy level that pattern that Eugene mentioned, this geometric convergence to zero energy when you're at unitarity, at infinite two-body scattering length. And this is the pattern of trimer energy levels. Here, when they're below zero energy, you get the Efimov states, the infinite ladder at unitarity. At finite scattering lengths, these go and merge into the three-body continuum, and at that point they become observable in an ultra-cold gas as three-body recombination resonances. This is the infinite sequence of Efimov character shape resonances I alluded to before. One of the actually interesting puzzles in the community recently is why some of the experiments are seeing features at these points, because the ultra-cold gas is up here at this energy. And so you would think anything related to dimer physics, right, where a trimer merges into the dimer, atom-dimer line, you would think this is occurring at a different energy than in the ultra-cold gas. And there's an interesting preprint by Christian Langmack, who's here, with Eric Broughton and Smith, who point out a possible way that reason why one would see those resonances. It's interesting preprint, I think. To come back to the Efimov effect and how it works, again, the main point in the hyperspherical picture is there's a 1 over r squared potential energy curve, which would go all the way to the origin if you had zero range potentials, zero range two-body potentials, and of course no system has this 1 over r squared attraction all the way to the origin. If so, you would have this, what Landau and Lifshitz call the fall to the center problem, that you basically, the ground state energy in such a potential drops off to minus infinity. But assuming there is some short-range cutoff, which is usually viewed in most theories of Efimov physics up until about a year ago, or maybe 2 years ago now, was viewed as an arbitrary cutoff parameter. We'll see that in the case of the van der Waals two-body interaction, there is emerging a natural cutoff scale that happens really just as a consequence of van der Waals physics. And this is what I call the Bombshell Paper of 2011 by the Innsbruck group in collaboration with theorists Julian and Jeremy Hudson, that found that the three-body parameter, in essence, in this graph, this one, the position of the first Efimov resonance is really always occurring at the same place when measured in van der Waals length units. That was pointed out here, and it was a big surprise to me because we, like I think most theorists in the community, had thought it was going to vary quite a bit from one system to another. And there have been some other papers on this in addition to our PRL that came out last year. Cheng Chin has a toy model, and there is some work by Ueda, which is on the archive, not published elsewhere yet, which is also a hyperspherical treatment and pretty much confirms our conclusions, I think. There are some other, a couple of other papers as well bearing on this issue. So this is kind of a quick summary of the experimental evidence seen. This was in the Bombshell paper, the 4 Efimov resonances, all seeing the same approximate value for the value of the two-body scattering length, call it A minus, where you have a zero energy Efimov resonance, and always around this range 9 to 11. Randy Hewlett also had some a value in lithium. Lev Kekovich also in lithium, and for potassium, there was at one point a value that seemed not to fit the pattern, but that experiment has been redone, and I'll show you some of their data later, which is now, their newest data is consistent with this pattern as well. And then there was one data point in 85 rubidium from the Gilla group that they published last year, which also fits the same pattern. Looks very universal and not just sort of a random occurrence of this first Efimov state. So we set out to interpret this using our hyperspherical toolkit. Especially this was in Jia Wang's PhD thesis, this is one of the figures. And so we tried to make our calculations get increasingly sophisticated, include more and more two-body bound states. This has a negative side that it produces a mess like this, a huge set of adiabatic hyperspherical potential curves that might look rather hopeless. You can kind of draw a locus of diabatic crossings through these potentials. And when you look at this, you might think, well, this is, just too much information. This can't be really relevant to this simplicity coming out in the Efimov problem. But don't forget, the Efimov physics is all right here around zero energy, very, very compressed to the three-body fragmentation threshold. So now to really make any headway about seeing how this connects to Efimov physics, we don't care about these non-universal states down here. Let's focus on this, the states very close to zero energy. And do the recombination calculations. This required a real tooling up of our ability to solve these many-channel three-body recombination rate coefficients, a lot bigger calculations than we had done before. But you can see the green and the blue are two potentials that have a van der Waals tail. And for different numbers of S-wave bound states, up to 10 S-wave bound states, I think that last example I showed was around 10 S-wave bound states, and a total number of two-body states around 100, including all the orbital angular momentum states of the dimer. You can see they do, in fact, fall in this region between around -8 and -11. On the other hand, the Sech squared potential, which is more like a potential energy, I guess, that would apply to a nuclear system, it does not show the pattern as if we kind of make an equivalent van der Waals length by equating the effective range to what the effective range would be for a van der Waals potential. We can put this on the same scale for a Sech squared. And for a few numbers of bound state potentials, like a nuclear system, nucleon interaction, it doesn't quite fit this pattern. But it seems it sort of does if you get deeper and deeper and have many two-body bound states. It begins to resemble the same pattern. So this was first sort of confirmation. Okay, the theory is predicting this is consistent with this observed universality seen in the Bombshell paper. But now we had to interpret that, what was really going on. And one of the things that we were really starting to focus on is the fact that anytime any two bodies come together at low energy in this three-body system at low energy, it's like they're going over a cliff, really, because the van der Waals potential goes down so steeply compared to, say, the de Broglie wavelength. One thing you might imagine is that it might be a quantum reflection idea, sort of like Eugene was mentioning in his talk. And we actually investigated quite a bit this possibility by looking at the wave functions near the van der Waals, the cliff. And in the end, we found that it doesn't really fit the pattern of the quantum reflection. You have to really be at very low kinetic energy to get this quantum reflection effect. And we really found it's really pretty classical. It's just like, going over Niagara Falls in a barrel. It's really a classical effect but nevertheless, there is a suppression of the wave function in the two-body valleys. And it's kind of nicely illustrated by looking at the wave functions near this van der Waals radius point. For a case where you don't have the van der Waals potential, which is shown here. And these are the two-body valleys that have a lot of wave functions sticking out in them. Whereas if you have the van der Waals two-body interaction at long range, you see a huge suppression. And I sort of like to think of this then in the language we use in our paper is that it's like a classical suppression. Just the fact that the probability for two bodies to be within between r and r plus dr goes like 1 over the velocity. And as you go over the cliff, the velocity got so high that this v has increased so much that the wave function in the two-body valleys, in other words, you just zip in and zip out so fast, your kinetic energy grows so high. And that, in hyperspherical language for the three particles, it means there's a huge increase in the hyperspherical potential curve, because this has that angular kinetic energy, hyperangular kinetic energy. And so this is the key graph, I think, that sort of showed us why you have a universal behavior. That all of the systems with 1 two-body bound state, 2, all the way up to 10 S-wave bound states, all of them in the Efimov channel, they have a barrier at twice the van der Waals radius. Okay, that sets the scale. Yeah?
You allow me a naive equation.
Sure.
Your argument that it accelerates, okay, but if you go on with your classical image, then it will bounce. And at the moment when it stops, then the probability is quite large. So how do you manage?
Well, usually these are pretty steep. It's almost like a vertical wall. So yeah, it bounces, but I think it's, you know, the inner wall of these two-body potential curves is very, very stiff. That's my picture, but I agree it's pretty qualitative at this point, and it'd be nice to study that short range. Yeah.
What would be different if you had quantum reflection?
Well, if you had quantum reflection, then you wouldn't even really go all the way into these small distances in the two-body sector. Basically, as the two particles start to move into the valley, they would never even go there at all. But we think they really do go there, but they have so much kinetic energy, it shows up as an effective barrier in the hyperradial potentials. So that it's certainly a different picture, and maybe there's a way to test that, but we haven't really thought of a way to really do say an experimental test of that point. So in the end, we can make sort of a universal, within the context of van der Waals two-body interactions, a universal barrier. And in the paper, we give an analytical form for the effective potential. The main thing is that it is deeper at short distance than the pure Efimov potential. That's this dashed green curve, which you can sort of splice on, if you like, to a 1 over R6 potential. But that's not so relevant, we think, to the physics. That's a little bit more like what is going on in Cheng-Chin's model. That this is the relevant potential curve. It's more attractive, reflecting the van der Waals physics here, but it has a barrier reflecting this classical suppression here. So when we did this calculation, it was all with single-channel two-body potential models. In other words, we don't include all the hyperfine substructure that the real alkali atoms have. And that's a bit of a worry that maybe this would break down everything I've said when you include that multi-channel nature. And one way to test that is to look at resonances, Feshbach resonances of different widths. Basically, the lore in the field is usually that one thinks these single-channel models should work pretty well if you have broad Feshbach resonances. But they'll begin to break down, one expects, if you have narrow Feshbach resonances. And there's a resonance parameter that quantifies whether a given Feshbach resonance is narrow or broad. And in particular, in this new experiment that's just gone on the archive a week or two ago, a range of different Fano-Feshbach resonances from broad to narrow have been studied. and 7 different Efimov resonances attached to 7 different two-body resonances in 39 potassium have been observed. The interesting thing is that these are the raw data. They see, all of these are the Efimov resonances they're seeing. I guess there are 7 of them, all the way from narrow 0.1 up to broad 2.8. And the interesting thing is they all, you can kind of already see in this graph, they're all occurring at fairly similar values of the two-body scattering length. And if you actually plot then the A minus in van der Waals units for their data, you see they are all clustering within their experimental error around this expected value around -10. So it looks like this van der Waals potential may be controlling things more than one would have expected, just from the validity, expected validity of the single-channel two-body interaction model. And we'd like to understand this better and see, one would think when one gets to very narrow two-body resonances, this would break down at some point. But it appears that that point has not been reached. Maybe there are signs that it's starting to be reached for the very narrow resonances, but it's not a huge deviation from the expected pattern. I just wanted to mention briefly that there is then Yujun Wang, senior author, PRL, late last year on extending all this to the heteronuclear systems and seeing sort of 2 different categories, whether it's sort of Efimov favored for the heavy light systems or Efimov unfavored for the light heavy systems. And he does see a universality for this. But the parameter space is quite a bit more complicated. It's not just one number, because it depends now on mass ratio. It depends on the 2 different van der Waals lengths in the problem. And it depends on the background like atom scattering length. But he has mapped out some of the universality predictions in that paper. They do seem universal, but it's not as simple a story. Okay, yeah, this just summarizes some of that, but I think I want to move on to talk about the D-wave resonance, which is maybe a little bit more in keeping with the spirit of this particular workshop. The higher energy physics in 2 bodies or 3 bodies begins to probe higher partial waves. Everything I said so far is focused on S-wave interactions and J equals 0 states. So one of the things that I thought was really interesting that we learned from Bo Gao's work on 2-body physics in a potential with a van der Waals tail is that if you have a resonance at 1 partial wave, L0, for 2 bodies, 0 energy state, there will be another one close to 0 energy in L0 plus 4. And of course, for homonuclear systems, only the even L's are going to appear. And so what you might think is that, well, midway between these, at L0 plus 2, you would expect a state to be sort of midway between making a new resonance. Okay, so in other words, you're likely to have the partial wave, say, between where 2 L's have a resonance for S wave, you might expect there to be a D wave. Like if there's an S and a G wave resonance, that for the D wave you would have a resonance occurring at small 2-body S wave scattering length. Okay, I think I said that in a very puzzling way. But I think it'll be a little clearer when I show some of the results. Okay, so for instance, there will be a value of the S-wave scattering length at which you have a 0 energy D-wave resonance. And it should appear at smallish values. In other words, not at values of A, S-wave A, that is very large compared to the van der Waals length. It should be appearing more, in fact, very close to A, approximately equal to the van der Waals length. That you should get a D wave and also an I wave resonance. There would be another one. So three-body recombination near these points had not really been studied, and this was one of the things Jia Wang investigated, again within the context of a single-channel broad Feshbach resonance model. So what he calculated was looking at the two-body D-wave state as it comes up, as you vary the S-wave scattering length for a system, how a D-wave state tracks that and goes to zero energy. And you might expect at that point to see a three-body resonance, at least near that point. And on this plot here, he's calculated at a rather hot temperature for ultra-cold standards, 127 microkelvin. Here is the point where the D-wave state merges to zero energy. And shifted away from that, he found a peak in the three-body recombination cross-section. And basically, he can interpret that looking that there is a three-body state that's sort of attached to this D-wave dimer shown here. And of course, the three-body state merges into the three-body continuum at a slightly shifted point, around 10% away from where the two-body state goes to zero energy. And interestingly, it produces, at least in this calculation, and it seems fairly universal, for single-channel models, it produces a peak just below threshold where essentially you've got a D-wave state that's very, very weakly bound, very easy to recombine into. And, but also then you get the usual type of three-body resonance where the three-body state itself goes to zero energy. So I'm hoping someone can look for this experimentally. I think there's been one or two groups that have explored this, but so far no evidence for this. And again, it could be, probably the exact position will not fit the pattern of standard of a single channel two-body model. But that remains to be seen, how general these results will be as you try to go to multi-channel models. Okay, so let me turn to say a little bit about the n-body recombination problem. For instance, four-body recombination has now been studied, and there have been four-body resonances seen by a few groups, which are sort of correlated with the Efimov effect. And it shows up experimentally, especially as a four-body recombination reaction. Four slow bosonic atoms like cesium simultaneously colliding to make either two dimers or a trimer and an atom, or a dimer and two free atoms. All of those would be grouped into what we're calling the recombination processes. And of course, I'm interested also in maybe seeing examples of that in the nuclear system. We're just starting to hopefully move toward some calculations to explore that regime. So basically, we dove into this calculation. Seth was heavily involved in this, and found that the four-body energy level pattern looks as follows, that you get between each pair of Efimov trimer energies, let's say looking at the unitarity line where the two-body scattering length is infinite, between each two Efimov states, you'll find two four-body states. This is sort of a logarithmic scale, so it doesn't quite do justice to the scale of energies involved, but it does show this qualitative nature that you expect these two Efimov states, or two four-body states between each pair of Efimov states. And in particular, there are points that we were able to predict where the four-body states merge into the zero-energy continuum, where a gas of atoms you would see at this point, well, I guess it's over here, the two arrows, you should see four-body recombination resonances at these points, either at 0.43 times the two-body scattering length, where an Efimov three-body resonance is seen, that would be this state, or at 0.9 times the two-body scattering length, where a three-body Efimov state is observed. And then this is how it looks in the hyperspherical picture. You get a four-body hyperspherical potential curve which converges at infinity to each Efimov state of the system. And it's really quite simple. It's amazingly simple. And this is just deep enough to hold 2 bound states in each of these wells. And that doesn't change really when you include the non-adiabatic coupling effects. And so we're talking here about a recombination process that looks more or less like this: 4 atoms simultaneously colliding in the gas and then forming clusters, in this case 2 dimers, which in the hyperspherical picture looks like coming in on this 4-body entrance channel, doing some non-adiabatic coupling, and going out to infinity in some of these bound channels, 2-body channels. So as we started to look into generalizing this to actually try to do a 4-body or higher number of particles recombining, we noticed that in this region of negative 2-body scattering lengths, all of these are starting to look like they fit the following pattern, that you have a repulsive barrier which is controlled only by the number of particles. We wrote it here as LE plus a half, an effective angular momentum barrier. And this is a simple function of n. And it involves the 3-body reduced mass and the hyperradius. It's always guaranteed to be repulsive in this channel at long hyperradii. But there are resonances due to the short range attraction. There is a lot of 2-body bonds that are attracting in the system, and they can make quasi-bound states that live behind this barrier, which are these states that are showing up as resonant enhancements of 3-body recombination. And then there will be recombination channels that are non-universal in general, and so there will be some coupling, non-universal coupling that we can't really predict for realistic systems yet, that takes the incident flux that did tunnel in, feel this resonance, and then escapes to infinity in these bound 2-body channels. We had a paper which was a bit of scattering theory, which was fun but more challenging than I expected, to simply derive the n-body recombination rate coefficient. And it's just the kind of formula that a theorist has to love with gamma functions and shit. Okay, I already showed this graph. Okay, so here's some experimental data. And this is actually data from the Innsbruck group at the time they had their Nature paper on the 3-body Efimov resonance. That's this peak here. And when we looked at their data at some different temperatures, we saw that, in fact, right at the point where we predicted a 4-body resonance, they had a little extra feature in their data. And this was part of the reason we decided we needed to try to make a quantitative calculation of 4-body recombination, because if you just include 3-body theory, it doesn't show any enhancement here. But in fact, when you solve the coupled equations and you find that you can represent this resonance feature, there's no adjustment in the position. It's coming out right where this analysis predicts it at about 0.43 times the scattering length at which the 3-body Efimov state appears. And there's even a little hint of an depending on how generous you are, of the second 4-body resonance here. There's even a hint of that in the experiment. It's quite clear in the theory. But then Javier von Stecker, after he finished his PhD, he started to look at more than 4 particles and started to look at, well, let's see how far this picture can go. And I guess this is moving toward heaps now, okay, in Selim's language, having 5 bosonic atoms, 6, 7, and 8, and looking at the energies of those as you vary the 2-body scattering length in some units, like van der Waals units or something like that. And he found that, okay, in addition to the 3- and 4-body resonance going to 0 energy, their 5-body does, and 6, and 7, and 8, and these are really following the universal pattern. And he went all the way up to 13, and he could predict the scattering lengths at which, if you know the 3-body scattering length where there's an Efimov state, he could tell you where there would be a 4-body resonance, a 5, and a 6. And you can kind of think the attraction in the two-body sector is increasing as I move in this direction. So there's a point, like right here, where the attraction is enough to bind 8 particles, but it's not enough yet to bind 7, 6, 5, 4, 3, or 2. Okay? And then if you make it a little more attractive, okay, there's a point where you could bind 7 or more particles, but you can't yet bind 6, 5, 4, 3, and so on. So it's pretty interesting to see this systematic evolution of states. And of course, what I showed so far is only the n equals 3 and 4 points. But now this has been investigated in Innsbruck, and they've looked for an n equals 5, a 5-body recombination resonance. These are the actual predictions, in particular, updated in a PRL by Javier von Stecker a couple of years ago. For, again, here's the 4-body resonance. He's predicting 5 and 6 and so on for different numbers of particle resonances, again, all the way up to 13. Predicting binding energies and scattering lengths where you would see these particular signatures in a recombination experiment. Okay, so, well, we were thinking we would like to solve this Schrodinger equation and find that box that could predict the hyperspherical potential curves for 5 particles. So, well, you might start writing down the Hamiltonian and then saying, well, maybe that's too hard. We weren't quite ready to find a way to solve the 9-dimensional Schrodinger equation once you've eliminated center of mass and the angular degrees of freedom. So we resorted instead to the Mulliken style potential of using what we knew about the topology and trying to back out the crucial information about that potential barrier, which is the rate limiting step for the recombination process. And so we knew it had to have this potential curve, had to have this topology. And if it's in a spherical trap, okay, that will add a trap potential to that. And what Javier realized was, well, he can use correlated Gaussians to diagonalize the full system and find energy levels as he changes the trap strength or as he changes the two-body scattering length. And basically, you'll get trap levels and you'll get that change as you change the trap frequency, and you'll find bound state or quasi-bound state levels that are these flat sort of stabilization type levels, and the strength of these avoided crossings between the inner and the outer levels is actually telling you about the tunneling through that barrier. So from that analysis, he could work out backwards what is the tunneling integral through this, and deduce the nature of the 5-body recombination rate, basically with just one adjustable parameter, which is the unknown decay down to the non-universal, like 3 plus 2, 2 plus 2 plus 1, and so on states. Okay, so this has been on the archive for a year as we battled with various journals trying to get this published. It was recently, I found out, accepted for a new journal of physics. This is like just some of the kind of coarse loss data that they see in the Innsbruck group as they look for these phenomena. They see a peak in the loss at the 3-body recombination and 4, and they see a hint of a shoulder that looks very suggestive for a 5-body recombination resonance. When we analyze the data a little bit more carefully, we can take their total loss data and, for instance, plot a curve which only includes 3- and 4-body losses, that's this green dashed curve, or only 3-body losses, or if we add the extra loss due to the 5-body recombination, it does, for their density conditions, it does produce this extra shoulder, which, at least to me, it looks very consistent with this expected pattern. And it seems pretty clear evidence that they have reached a regime where, for some range of densities, actually 5-body recombination is the dominant way that losses occur, that recombination occurs in this gas, from 5 bodies simultaneously colliding. To me, it's rather remarkable that they could see this experimentally. And it's encouraging that it fits the theoretical pattern. Okay, this is kind of just a blow-up of sort of Javier's analysis of these energy levels, again, which was used to deduce the tunneling parameters through that barrier. This is, again, just a blow-up trying to separate out separately the four-body recombination, and if you only include four-body theory, and then try to identify and isolate the five-body recombination part in the theory and experiment. One last topic I wanted to cover briefly is something really pretty completely different, looking at generalizations of confinement-induced resonances of the type that Maxime Olshany was exploring some years ago. In his work, he had a transverse harmonic oscillator confinement, and he was able to map out and find the values of the three-body scattering length, where you get in the effective one-body coupling constant for interactions that diverges, okay, and looks just like, for many-body physics, like a Fano-Feshbach resonance does in 3 dimensions. And this was generalized as well using frame transformation methods by Dorte Bloom and Brian Granger some years later, and applied to fermions where the three-dimensional scattering is P-wave rather than S-wave, as in the case that Maxime treated. We've been kind of curious about how this generalizes to other sorts of transverse geometries, and a PhD student of mine who will probably graduate later this year has applied this to a square well confinement in the transverse direction. Well, you might ask, why a square well? You know, the experiments aren't really doing a square well in the transverse dimensions, but we think it's interesting as a first step to generalize to more complex geometries. And some of the interesting mathematics that comes out, for instance, in the Olshany work, is this divergent summation. And an even more divergent summation shows up in the Granger-Bloom treatment. But I kind of view these the way maybe Michael Berry does, that, you know, a convergent series is way too boring to be very interesting. Okay, who wants that? Okay, we like divergent series. Michael Berry told me when he was visiting Gilles some years ago that, you know, he loves divergent series much more than convergent series. And the interesting thing is that you can map these onto zeta functions, with the structure of zeta functions. Of course, this is a normal convergent series for s greater than 1, but it would diverge if you apply it to these situations. But you can analytically continue these, and there are some tricks like rewriting the summation in this sort of a form, which allow the analytic continuation. It's sort of like in the Casimir effect, where you start with a divergent positive calculation of the Casimir energy, and then after renormalizing, you get a finite negative number. Well, I always thought that was really, really cool, although somewhat mysterious. So anyway, Chen Zhang applied this to the same sort of logic, but now you have nx and ny. You have these two quantum numbers in the square. Of course, you don't have separation of center of mass and relative coordinates in this problem. So we've decided to treat a particular case where it's light-heavy scattering and the heavy particle is pinned to the center of the square. But then within that, we can treat that problem, and that leads to a similar sort of divergent expression. It's a generalization, more complicated than the Hurwitz zeta function. It's called the Epstein zeta function. And looking through the mathematical literature and doing similar renormalization tricks to what worked for the Hurwitz zeta function, Chen Zhang was able to calculate this and predict the value of the ratio of the three-dimensional scattering length to the length of the square side, at which you would get a confinement-induced resonance in this system. And interestingly, I haven't really understood. It seems like it's maybe just a complete random coincidence, but the value of the the side of the square over the three-dimensional scattering length where you get a confinement-induced resonance. This is confirmed by these points, which are numerical calculations, which we did because all this regularization of infinite series made me nervous. Anyway, these calculations did confirm the analytical result, which is down here, that you would get this. When you divide this number by 2, you get the exact same number, well, exact to 3 decimal places, to what you found in the two-dimensional oscillator confinement. So that's probably just a random coincidence, but it seemed rather curious to me. It's not too surprising it's of that same order of magnitude, but the fact that it would be the same to 3 decimal places, I have no reason to expect that to come out. So anyway, just to give a quick summary, we think now we understand how three-body universality extends, and it's not completely universal the way the Efimov effect is itself, because it does hinge on van der Waals forces. And you don't expect this to tell you exactly where that Efimov state should appear for a 3-nucleon system, for instance. But anyway, for atoms, for all the atomic systems of interest in the cold atom community, it does appear to be quite universal within about a plus or minus 15% error bar range of that A minus over the van der Waals length. And I think it's really interesting to pursue this track of making bigger and bigger heaps and seeing how these resonances show up in recombination and see if this trend predicted by Javier von Stecker extends to more particles. So with that, thanks for listening. Oh, the one of Javier? You don't mean this one. The number of bound states. Oh, this one. Yeah, okay.
So there's a line, the black line in the middle there is flat, right? So it says, so that's hard. What's that? That's van der Waals potential with some kind of short range wall on it?
Yeah, I think.
Why is it a flat line as compared to the others, which are actually?
Oh, okay. The flat line was a. I'm trying to remember how Jose drew that. He had a model which is just hard sphere, straight line, and then drawing the van der Waals potential. I think it's not really done separately for separate ends. I think it's just more like his estimate of what the asymptote is, or maybe it was done for the one bound state. Actually, I don't remember now exactly what the solid line is. Yeah, I'm pretty sure it's not a number that was recalculated for each end.
No, but that's not what I'm asking. I'm asking why is one line completely constant here?
Exactly constant. Yeah. Yeah, it's not really been redone for each end, I'm pretty certain.
For the 5-body recombination dominating process, does it follow a 8 to the 10th like curve as you increase scattering length? It goes up. Then for 3-body, it's 8 to the 4th, and then for 4-body, it's 8 to the 7th.
At least in the formula, it does, right, Seth? I don't remember if I wrote the formula. I think I did write the formula. Oh, no, but I didn't. Yeah, we have this goes like Ka to the 3n minus 5, right? This S, this dimensionless S matrix. And let's see, 3, yeah, that's A to the 10th, yeah.
I actually had one about this. I assume in your for your universal van der Waals number, this A minus equals 9.25. Van der Waals, when you increase the number of bound states, that's just the number of S-wave bound states. But you include like the D-wave bound states.
Yeah.
If you
Well, like have a
S-wave
projection operator only onto the S wave. That I don't know, but I should maybe have mentioned that in that calculation, we did not include all of the two-body bound states. Jia sort of went down, including some number and then going a little further down, and he could really see convergence as he included more and more coming down. But his calculations did not really include all of the low-line potential curves.
I guess I was wondering, because if I remember properly from your paper, this short-range boundary is actually a whole bunch, a series of very narrow avoided crossings. It's really a diabatic, or is that a true adiabatic you showed for this universal?
I think I don't recall that there were curves cutting. Maybe every now and then you would find one cutting through, but for the most part, that was a pretty isolated potential curve. But I will say the diagonal, I should have maybe mentioned this also, the diagonal correction is important. If you don't include that, and this point was stressed in the UATA paper also, if you don't include that, this potential goes an order of magnitude deeper, which shows there is a lot of kinetic energy in hyperangles and that's affecting this dynamics in an important, non-trivial way.
I just want to make one quick comment about quantum reflection. Both appear in my your talk. In my case, though, I was referring to the quantum reflection in the Fourier direction in different regimes, which does not contradict to your interpretation of the classical picture for the university body.
So you really looked at, you were getting quantum reflection at the barrier. That should only happen just above the barrier, though. Just at energy, just barely above it.
The thing is that quantum reflection was more about the kind of two-body equivalence, or like a kind of van der Waals interaction. When you have two different linear combination of solutions from certain potential, when the WKB approximation for the wave function breaks down, then that's the place where you get quantum reflection. So that's a different from.
Yeah, I'd like to see your measures of quantum reflection and sort of see if you're looking at it the same way that Jia and Jose and I were when we did that other study.